In the last class, we have formulated the principle of WKB and have seen the criteria for the validity of WKB method. Now in this class, we will consider a general expression for the WKB wave function that will help us to write the wave function representing the problem under our choice depending upon some standard parameters associated with the particular problem. We have already stated that WKB is an approximation method suitable for stationary problems or time-independent problems. So that in considering a general expression for WKB wave function, we will of course limit our discussion in the regime of stationary problems. As you know, or as you have developed from quantum dynamics, in the case of stationary problems, the wave function can be taken as the product of a space-only dependent part, which is being represented as a phi of r here, and a time-only dependent part, which is being represented as a chi of t. Where this time-only dependent part will generally have a format in terms of the energy eigenvalue E as, say, exponential minus I by h cross energy into time. And in the regime of WKB method, we will be then interested in this space-only dependent part, because WKB is a method suitable for stationary problems, and hence we are interested in the space-only part of this wave function. And if you are interested in writing the entire wave function representing the system at any instant of time, you just require to multiply the space-only dependent term by means of the general expression for the time-only dependent term. So it is this part of the wave function in which we are interested. And of course, phi of r will generally have a formulation in terms of the space-only dependent part of the action, as we have seen while we talked about the principle of WKB method, which is a W of r, or which for the time being I will be representing it as a W of r. So phi of r will have a general formulation exponential I by h cross W of r, such that the total action representing the semi-classical system may be written as S of r comma t equal to W of r minus energy into time. This also gives an illustration of the separable nature of the space-only dependent part and time-only dependent part of the stationary quantum states. So clearly W of r is the space-only dependent part of action, and energy into time represent the time-only dependent part of the action. I will not be specifying it as a classical action or quantum mechanical action. If we are writing an expression on the basis of the classical equation of motion, generally we will be taking this as classical action that will have only one constant component, which we have already represented as, say, S0. Corresponding to such a classical action devoid of any component in terms of the exponential series, in terms of the different powers of h cross, there will be only one constant space-only dependent part for this classical action that I will be representing W0 in the subsequent discussion. And if we are making a comparison with a quantum mechanical system for the real system, then the action will be represented as, say, S. And from the principle of WKB that we have just formulated, we have seen that this action will have so many steps, or this is most suitably represented by means of a series expansion in terms of different powers of h cross. And in the limit of WKB method, we will be contented with the first two terms, S0, a constant part, plus h cross by I, that is the term containing h cross as long as the semi-classical approximation is concerned. H cross by I is 1, where S1 is the first coefficient of the first power of h cross, or the term having h cross with a power 1, because this term will have h cross having a power say 0. So corresponding to S0 and S1, there will be two different parts for the space only dependent part of action W, that I will be representing as say W0 plus h cross by I W1. That also goes with this general expression for the total action. So now we will be interested in identifying W of R, so that we will be able to write the wave function, that is WKB wave function, in the format phi of R equal to e raised to I by h cross W of R. So the problem has now decomposed into the problem of identifying W of R in the semi-classical limit, or in the limit of the WKB approximation. So that simply by putting W of R in this expression, we will be able to identify the general expression for WKB wave function. Clearly, I have mentioned you W of R will be equal to W0 plus h cross by I W1, h cross by I W1. So now our problem involved the evaluation of W0 and W1, so that we can write W equal to W0 plus h cross by I W1, substitute that value of WR in this general expression. That will give us a formulation, or a general formulation of the WKB wave function. Of course, then for that the mode of operation will be, first of all, the evaluation of W0 and then the evaluation of W1. Where shall we get these parameters W0 and W1? Of course, we can have them from the corresponding differential equations in W0 and W1. That equations could be obtained from the classical equation of motion that we have written in terms of action, and the quantum mechanical equation of motion that also we have written in terms of action. While we talked about the principle of WKB, the classical equation of motion is given by minus dou s by dou t equal to grad s whole square by 2 mu plus v, where s is the classical action. Better I might have represented this as say S0, but earlier I have represented it in terms of S only, and it was stated that it is the classical action. Here also I will be using the same representation, such that S in this equation represent the classical action, and in the subsequent equation the same symbol will be used to represent the semi-classical action, or action within the regime of the validity of WKB method. Now we substitute S equal to W0 minus Et as long as this equation is concerned. Clearly minus dou S by dou T will be equal to, this part is space only dependent, it has no significance as long as a differentiation in time is concerned. So that derivative of S with respect to time is minus E. So minus dou S by dou T is equal to plus E. And grad S will be, grad as you know is a space only dependent differential operator. And again we will be limiting WKB, for we have already seen that WKB will be generally applied in the case of one-dimensional problems, or problems that could be decomposed into the sum of one or more than one-dimensional problems. So here also in this general formulation, I will be considering WKB in one dimension, that's along the x direction. So grad S has the meaning of d by dx. So grad S in this case will be dw0 divided by dx. Substitute these values of minus dou S by dou T and grad S in this expression, we will get a homogeneous differential equation in W0 the classical part of the space only dependent part of the action. And this is given by E equal to, we have substituted minus dou s by dou t equal to E equal to 1 by 2 mu grad s whole square. Instead of grad s, I'll have dw0 by dx whole square plus v. For writing it in the format of a homogeneous differential equation, for that you'll have to multiply the entire equation by 2 mu and take the term 2 mu into E from left side to the right side, and the first term will be then appearing as dw0 by dx whole square plus 2 mu into E from the left side being fetched to the right side become minus 2 mu into E, and already I have plus 2 mu into V on the right side. I have taken a minus out to make it say minus 2 mu into E minus V of x equal to 0. Take care of this quantity 2 mu into E minus V. This will have a particular representation. I'll tell you it very shortly. For the time being, it is E minus V is the total energy and V is the potential energy. So E minus V is definitely total energy minus potential energy. And for the WKB system, we have taken the total energy to be the sum of the potential energy and kinetic energy. So the quantity in this bracket is nothing other than the kinetic energy, and I am multiplying kinetic energy by means of 2 mu, which is nothing other than the momentum possessed by the classical particle or the classical momentum. So this equation will be my implication for the solution towards a W0, and I require W1 also, so that I will be able to take the total space only dependent part of the action possessed by the WKB system. Then I'll have to find another equation for W1. This, of course, we can obtain from the quantum mechanical counterpart of the classical equation that we have already seen. The quantum mechanical equation is minus dou s by dou t. Here S is the quantum mechanical action or the total action. I must tell it the total action. And once I put this to be equal to, say, accuracy to the first two terms, then definitely this will be the action within the limit of the validity of WKB method. So the quantum mechanical equation is minus dou s by dou t equal to grad s whole square by 2 mu plus V minus IH cross by 2 mu del square S. Here S is clearly W of R minus ET with W equal to this series expansion or being represented by this series expansion. So we substitute these values of minus dou s by dou t, say grad s and del square s. Here also minus dou s by dou t equal to space derivative of this s, that's equal to E. Grad s is nothing other than dw by dx. Take care of this quantity. W is not simply a single term, it contains a series expansion. So we substitute here minus dou s by dou t equal to E. 1 by 2 mu is written here. D grad s is nothing other than dw by dx. So we substitute it dw by dx whole square plus V minus IH cross by 2 mu. Del square S is nothing other than del dot grad S. Del dot grad S will be then the second derivative of W with respect to X. This equation also we write in a standard format. For that we take we multiply the entire equation by 2 mu and take the quantity from the left side to the right side. Then this becomes 2 mu into this quantity, 2 mu vanishes, dw by dx whole square, plus 2 mu into E from left side is taken to the right side to make it say minus 2 mu into E. Already on the right side we have 2 mu into V. 2 mu here in this term, third term also vanishes to make it say minus IH cross d square W by dx square. And I have forgotten to put or equate this to say 0. Now we rearrange them. dw by dx whole square minus 2 mu is taken as a common factor from these two quantities. This also converts to momentum of the particle. Minus 2 mu into E minus V minus IH cross d square W by dx square. And the Schrodinger equation IH cross dou psi by dou t equal to minus h bar square by 2 mu del square plus V operating over psi. This derivation of the WKB Wave function phi from the action, with action being first of all represented in terms of its different space only dependent components corresponding to the classical regime or the quantum mechanical regime, W0 and W1 respectively, may seem awkward because we have a direct method of deriving the wave function in quantum mechanics, and that is in fact the most fundamental nature of quantum mechanics, that involves the derivation of the wave function by formulating the Schrodinger equation satisfied by the wave function. However, this method that we are going to represent here or present here has some mathematical ease as long as the derivation is concerned. However, we can show that this derivation is consistent with the other possible derivation of the WKB wave function by solving the Schrodinger's equation. Both these procedures are consistent. For that, let's consider the Schrodinger's equation IH cross dou psi by dou t equal to minus h bar square by 2 mu del square plus V operating over psi, with psi having this representation involving the separated space only and time only dependent parts, respectively phi of x and chi of t. That becomes, so we'll have to substitute dou psi by dou t and del square psi. Dou psi by dou t is evaluated here. Psi is phi into chi, and psi phi and chi are given. Dou psi by dou t will then involve the time derivative only, that involves the differentiation of the time only dependent part, which is chi of t. Upon differentiating, we get it say minus I by h cross into E into exponent has a differential, that is the exponent function itself, into phi, that is phi into chi, make it say psi. And del square psi is evaluated here. Grad psi equal to I by h cross into psi. Del square psi is essentially del dot grad psi, that's equal to del dot phi into chi, that's equal to del square phi into chi. Substitute these values here. We obtain this IH cross into minus I by h cross E psi equal to minus h bar square by 2 mu into del square phi in one dimension has the meaning d square phi by dx square plus V operating over phi into chi. Chi is also written here. Dividing the entire equation by chi, we make it say E psi. Psi involve phi and chi. Chi vanishes to make it say phi only. I into minus I square, which is plus 1. H cross vanishes. On the left side we have only E phi equal to minus h bar square by 2 mu d square phi by dx square plus V phi. For rearranging this in the format of a homogeneous second order differential equation, d square phi by dx square, we multiply the entire equation by means of 2 mu by h cross square with a minus sign, minus 2 mu by h cross square, so that we will get t square phi by dx square as the first term. And on the right side, minus 2 mu by h cross square V remains. On the left side, we will have minus 2 mu by h cross square E remaining, taking that term to the right side to make it say positive. So overall this becomes 2 mu by h cross square into E minus V into phi, that's equal to 0. So by solving this one also, we can have an evaluation of phi, which is the WKB wave function. And we will be using both of these to solve the WKB wave function. So from the classical equation, we have already obtained dw0 by dx. Here we have taken only the space only dependent part of action applicable in the case of a classical system, or in the classical regime rather than a classical system. In the classical regime, minus 2 mu into E minus V equal to 0. I have already told you this is nothing other than the square of the momentum. Total energy minus potential energy is E minus V. That is kinetic energy. When it is multiplied by twice the mass, that will give you the square of the momentum. So dW0 by dx whole square equal to P square, where small letter p is being used to represent the instantaneous value of momentum possessed by the particle. Schrodinger's equation then becomes d square phi by dx square plus p square by h cross square, because here the coefficient was 2 mu into E minus V. P square by h cross square phi equal to 0. And this has a solution phi equal to e raised to I by h cross w of x, which is the assumed solution with which we have started this derivation. And with W being equal to W0 plus H cross by I W1 within the limit of the validity of WKB approximation, or in the limit of accuracy that we require as long as WKB approximation is concerned. Actually, there are higher order terms in square and cube terms of h cross. However, we will be limiting, or we will be satisfied, or we will be contented with the solution up to, say, the first order. Consider the quantum mechanical equation represented in terms of, say, W. We have already obtained this as, say, dW by dx whole square minus 2 mu into E minus V. Once again, this is square of momentum, plus h cross by I d square W by dx square equal to 0. So our prime requirement to obtain the WKB solution phi involved the evaluation of W of x. And this W is given by W0 plus h cross by I W1. So now it is more straightforward. To find the solution, we have to evaluate first of all W0 and W1. After getting W0 and W1, sum up them in this format to obtain W, and substituting W in the expression for phi, we will be able to write down the WKB wave function, or the so-called solution. For that, we make a substitution here, because this is a second degree differential equation in W. To solve it in a more easy manner, this is also a procedure that you have repeated several times in your mathematics classes. Make it into a first order differential equation. For that, you will have to substitute, or we substitute u of x equal to w by dw by dx. And rearranging this equation, I leave this term on the left side and take all the remaining to the right side. Then this becomes h cross by I d square w by dx square becomes d by dx of dw by dx. We substitute d by dw by dx equal to u of x. Then this is first order in u. So the second order differential equation in W is turned to be a first order differential equation in U. D square W by dx square is written as a du by dx equal to minus 2 mu into E minus V upon taken to the right side becomes 2 mu into E minus V, which is momentum square. And we already have plus dw by dx whole square on the left side. Taking this to the right side, with a minus sign, this becomes minus dw by dx whole square, that is minus u square, as dw by dx is substituted as u of x. Also, we know that w has an exact format, say this one, w equal to w0 plus h cross by I w1 plus h cross by I whole square w2 plus etc. And in the limit of WKB, or in the limit of the validity of WKB, we will be satisfied with the terms up to, say, this one. Now differentiating this, we get dw by dx equal to dw0 by dx plus h cross by I dw1 by dx plus h cross by I whole square dw2 by dx plus etc. That is u of x equal to u0 of x plus h cross by I u1 of x plus h cross by I whole square u2 of x, etc. Differentiating this again, because we have a du by dx term in the equation that is to be solved. Du by dx equal to du0 by dx plus h cross by I du1 by dx plus h cross by I whole square du2 by dx plus etc. Now substitute this value of du by dx in this parent equation. H cross by I du by dx equal to p square minus u square. That is h cross by I du by dx is substituted within this bracket equal to p square minus u square. U is substituted as u0 plus h cross by I u1 plus etc. whole square. Now comparing the coefficients of different powers of h cross by I on both sides. The zeroth order term, that is the term that do not contain h cross by I on both sides, but on the left side you have all terms containing at least h cross by I, so it is 0 on the left side, and on the right side however there is one term that is devoid of h cross by I, which will be p square minus, this is of the form a plus b plus c plus d etc. whole square, that is a square plus b square, that has an expansion as you know, a plus b plus c plus etc. whole square equal to a square plus b square plus c square plus etc. all these square terms followed by 2ab, 2bc, 2ac, because there will be ab and ba terms that will have a general format 2 times the product of these couplets, involving all the possible couplets. AB can be a couplet, AC can be another couplet, AD can be another couplet, like that it goes, plus etc. So considering that, we have the zeroth order term in terms of h cross by I on the right side as p square minus u0 square. So p square minus u0 square equal to 0. That means u0 equal to plus or minus p, the magnitude of momentum. Now the first order term on the left side, we have h cross by I coming in only one term, that is h cross by I into du0 by dx. So the coefficient of h cross by I on the left side is du0 by dx. And on the right side, we will have h cross by I coming in one term only. A square term will be u0 square, b square term will be h cross by I u1 square term, that involves second power of h cross by I. So the term containing h cross by I will be 2 into u0 into u1. We have a minus sign here, so that will be minus 2 u0 u1. We have already obtained u0, so we require u1. So u1 is equal to minus 1 by 2 u0 du0 by dx. And to write down w in the limit of w0 and w1, or in terms of w0 and w1, I only require u0 and u1. So I'll come to an end for this comparison of different powers of h cross by I, because I have already obtained the necessary terms that I require. So u1 is minus 1 by 2 u0 du0 by dx. But look at u0, it can have two different values, plus p and minus p. And corresponding to plus p, there will be one value for u1, and corresponding to minus p, there will be another value for u1. So u1 has two different choices. That means w can also have two different choices, because w is written in terms of u. So corresponding to u0 equal to plus p, u1 can have a value, we mark it say u1 plus, that's equal to minus 1 by 2p dp by dx, or u1 minus equal to minus 1 by 2p dp by dx. And corresponding to u0 equal to minus p, u1 minus is the second value, that's equal to minus 1 by 2 minus p d by dx of minus p. So minus vanishes to make it say minus 1 by 2p dp by dx. So u that is being written as, say, u0 plus h cross by I u1 can have two different values, though u1 can have only one value, as this argument is a little false. Thus, though u0 have two values, u1 can have only one value corresponding to both the values of u0, either plus p or minus p. u1 has value minus 1 by 2p dp by dx, because when p is, say, u0 is minus p, then minus dp by dx and 1 by 2 into minus p will be making it again, say, minus 1 by 2p dp by dx, the same as the value of u1 corresponding to u0 equal to plus p. However, due to the two different values of u0, u1 can have two different values. I mean, u can have two different values. U equal to u0 plus h cross by I u1 can have two different values. We represent them u plus and u minus. U plus is u0 plus h cross by I u1 corresponding to u0 equal to plus p, and u minus is u0 plus h cross by I u1 again corresponding to u0 equal to, say, minus p. So u plus equal to u0, you substitute p plus h cross by I u1, u1 is minus 1 by 2p dp by dx. So that is p minus h cross by I 1 by 2p dp by dx. We will rearrange this. See, 1 by 2p dp by dx is the derivative of natural log root p. Natural log root p is 1 by root p into root p has a derivative. See, d by dx of natural log root p. Natural log root p has a derivative. Derivative of logarithm 1 by what is there inside the logarithm, that is 1 by root p, and derivative of root is, derivative of root x is minus 1 by 2x root x, minus 1 by 2 root x. So this will have a derivative minus 1 by 2 root p. Make it overall having a derivative minus 1 by 2p. That is 1 by 2p dp by dx is there. So absorbing this minus, we make it, say, p minus h cross by I d by dx of natural log root p. Root has a derivative 1 by 2 root x. I think I have put a minus additional here. This only, say, 1 by 2 root p. So this is p minus h cross by I d by dx of natural log root p. Similarly, u minus equal to, you substitute u0 equal to minus p minus h cross by I u1 is once again minus 1 by 2p dp by dx. So this is minus p minus h cross by I d by dx of natural log root p. So we have two different values of u being obtained. But we know that u equal to dw by dx. And we are interested in w in order to write the WKB Wave function phi as phi equal to e raised to I by h cross w of x. W could be obtained from this one as the integral of u over dx. So w equal to integral u dx. Therefore phi equal to e raised to I by h cross w of x equal to e raised to I by h cross integral u dx. That is exponential I by h cross integral. U has two different choices, u plus and u minus. Corresponding to u plus, we write the solution as, say, phi plus, and corresponding to u minus, we write the solution as, say, phi minus. Then phi plus equal to e raised to I by h cross integral p minus h cross by I d by dx of natural log root p dx. That is e raised to I by h cross integral p dx minus integral d by dx of natural log root p. I by h cross and this h cross by I will be vanishing for the second term. I might have put this a different exponential. Anyway, this is now e raised to I by h cross integral p dx. That is being kept as it is for this part. However, e raised to integral d by dx of natural log root p is e raised to minus natural log root p. Integration vanish with, or integration will be cancelling with this differentiation to make it say e raised to minus natural log root p. So this term becomes e raised to minus natural log root p into this is retained as it is e raised to I by h cross integral p dx. E raised to log x is x itself. So e raised to minus log x is 1 by x. So this is 1 by root p e raised to I by h cross integral p dx. Similarly, you substitute u minus to obtain phi minus as a, here this will be minus going minus and this term will be retained. Here you will have a minus sign. 1 by root p e raised to minus I by h cross integral p dx. Now we make use of the superposition principle. If there are two different possible solutions, the most general solution will be a linear combination of the two, as long as the solution or the wave function or the fundamental quality of wave function in quantum mechanics is concerned. It always satisfies the superposition principle. So the overall WKB wave function can be written as a by root p. So this is the first solution and this is the second solution. We take a linear combination of these two solutions and write down the most general solution with a and b being the expansion coefficients. A by root p e raised to I by h cross integral p dx prime plus b by root p e raised to minus I by h cross integral p dx prime. So this is the general format of the WKB wave function. So once we come across a problem where we can apply WKB method, very shortly I'll tell you what are the qualities of such problems where the semi-classical approximation will be most effectively valid. We will be able to write the wave function representing the system in this format. For this we require a knowledge about the magnitude of the momentum possessed by the system. So once you know, so I have 2 points to make here. The first point, once you know the momentum possessed by the WKB system, you will be able to write down the wave function representing the WKB system or the system under your study in this format. Just put a by root p where p is the momentum, e raised to I by h cross integral p dx prime plus b by root p e raised to minus I by h cross integral p dx prime. And the second point is that look at the momentum. Or the wave function is being written in terms of an exponential function involving momentum. However, the momentum is given by p equal to square root of 2m into E minus V, where E is the total energy and V is the potential energy. We come across classical systems such that the total energy possessed by them exceed the potential energy. Then the quantity within this square root is positive. That means the momentum possessed by the system will be real. However, there could be some situations, not some situations, most often there are situations where the potential energy exceeds the total energy. So that E minus V will be negative, making the momentum possessed by the system negative. Making the momentum possessed by the system negative within the square root, that is imaginary. So the momentum can be real provided the system is a classical system. However, in the case of a quantum mechanical system, the momentum can be complex or imaginary. And depending on that, the WKB wave function can also have two different mathematical formats. Suppose this is real, then the exponent is e raised to I into a real quantity. That can have a de Moivre's expansion e raised to I theta equal to cos theta plus I sin theta. So under such a situation, that is under the situation where the system is a classical system or purely a classical system, the WKB wave function will be represented in terms of cosine function and sine function, and such a wave function always represent an oscillatory system. So there is a chance that the WKB wave function representing a system may be an oscillatory solution. However, in the case of a purely quantum mechanical system, this parameter in the integral in the power of the exponent term can be imaginary. So there can be an additional I coming from the momentum, making the exponent, the power of the exponent as say I square, which is minus 1. So then it will be e raised to minus, and here this can be e raised to plus as well. That cannot have a de Moivre's expansion, and under such a regime, the wave function representing the system will be either an exponential decay, exponential fall, or an exponential growth. So the WKB wave function can have two different choices. For pure classical systems where the momentum is real, the wave function will be oscillatory, represented in terms of cosine and sine functions. And in the case of a purely quantum mechanical system, the wave function will be exponential. Most often it will be representing an exponential fall, as this is also something we have seen several times. Hence, in fact, a quality of the quantum mechanical wave function. For such a system, the total energy will be less than the potential energy. Once it is the situation, the probability for finding the system in such a regime will be diminishing exponentially. So this idea is also consistent with the general WKB wave function that we have derived. So this is about the WKB wave function, or the representation of a WKB system using a general wave function. The wave function, you just recall it, a by root p e raised to I by h cross integral p dx plus b by root p e raised to minus I by h cross integral p dx. Now we'll see some physical situations where we will be able to apply WKB method and some general mathematics that are to be derived in the case of such situations.